To find NPD, we have to make a few more assumptions and use the depletion approximation. First of all, we assume the carrier statistics in the neutral end region is not affected by the bias voltage because the number added to it is minimal compared with the electron concentration already there. Secondly, we assume the depletion region is very small compared to the neutral regions, so that its thickness can be ignored. With these two assumptions, we can argue that NPD is just equal to the carrier concentration in the n-side neutral region with energy higher than ECP. This argument is reasonable because carrier concentration cannot have abrupt change over a small distance, and we assume the depletion region is very narrow. If you recall that at thermal equilibrium, ECP is equal to ECP0, and the number of electrons above it is just NP0. Now, the Fermi level is lowered by VA. And in the second week of this course, you learned how to calculate the carrier concentration relative to the original one when the Fermi level is shifted. The new carrier concentration, which will be NPD, is given by NP0 times exponential QVA over KT, where NP0 is the carrier concentration at the reference Fermi level and VA is the shift of the Fermi level. The sign can be a bit confusing, but as I know that NPD will be smaller than NP0, a negative number in the exponent is needed. At reverse bias, VA is negative, and therefore QVA will give a negative number. This is how I figure out the sign instead of going through the mathematical details. Now, all variables in the diffusion current equation are known. We can write down the current equation as shown here. Expanding NPD, you will get the following expression. Some common terms of the equations are taken out and grouped together. We will then get the following equations for electron current density. For holes, we can follow the same procedure to calculate the hole current density, and the final result is given by the following. Combining both, the reverse bias current of the PN junction is derived, and it is given here. We can further manipulate and simplify this equation, but let's do it after we derive the forward bias current.